तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
In the last class, we were asked to find out the common emitter amplifier output impedance resistance when the so called current source was not ideal. In the sense, we said that current source which is occurring between collector and base, it is a reverse bias junction. So, it must be having a high resistance across it of the order of mega ohms, tens of mega ohms. So, now if that resistance is there, we want to find out in general what will be the effect on the output impedance, which is determined by applying a voltage V naught here and finding out the current I naught. V naught by I naught is the output impedance. R naught by definition is V naught by I naught. When I apply a voltage at the output, find out the current taken at the output. Obviously, we can say that RC directly comes across V naught. So, RC is shunting whatever impedance comes at this point. If you had not had this RC, it would have been merely this capital RC. Because of this RC, there is some effect. Let us see what it is. So, we will call this as I naught prime. So, additional resistance shunting R naught is therefore equal to RC parallel R naught prime, we will call it RC parallel R naught prime, where R naught prime is nothing but V naught divided by I naught prime. This V naught, same voltage which is occurring across RC, but another current I naught prime. So, whatever is applied across RC is also applied across this so called R naught prime, and that is now taking a current of I naught prime. So, R naught is really RC shunted by another impedance which is simulated by the transistor output circuit. We would like to now know what it is. So, R naught prime is V naught by I naught prime. Let us now understand what it is. Given IE here, we have alpha times IE always, that is our standard equivalent circuit. If this is IE, the drop across this is IE times RE. The current in this therefore is IE RE divided by RB dash. Now, this RB dash is nothing but RB parallel RS, because the base is connected through a DC resistance of RB to ground. Further, the source resistance also is coming to ground from the base. So, parallel combination of RB and RS will be RB dash. So, effective base resistance to ground. So, this current plus this current is essentially I naught prime. So, I naught prime is IE this plus IE RE divided by RB dash. So, this is I naught prime. I want to find out V naught divided by I naught prime. So, now I have to get V naught in terms of IE, then IE will get cancelled. in that expression. So, V naught is this voltage, this is equal to, let us see, we would like to evaluate this current in this. This is alpha times I E. Is this clear? This current is alpha times I E, and I know the current in this, right, alpha times I E, okay, has to be subtracted from the total current, which is I E plus I E R E R B dash, then that will be the current in R C. This current is I E plus I E R E by R B dash. From this total current, I subtract this alpha times I E, that will be the current through R C. Now, once I know the current through R C, drop across this is that current into R C. So, I have found out the voltage from here to here. Okay. The current, total current is I E plus I E R E by R B dash minus alpha I E is the current flowing in this, okay. That into R C is the potential across this, and the potential across this is plus I E R E. So, this potential plus this potential is V naught. Okay. So, now V naught by I naught prime, therefore, is very clearly I E will get cancelled, okay. 1 plus R E by R B dash minus alpha into R C divided by 1 plus R E by R B dash. This is an important expression, okay, giving in general for you output impedance looking in from the collector of any transistor amplifier. Why I am saying is any transistor amplifier, okay. A general transistor amplifier can be considered as one with a resistance from emitter to ground and another resistance from base to ground. We already have a resistance from base to ground. Suppose you have a resistance from emitter to ground, let us say capital R E, then this expression remains essentially same, except that R E has to be changed to R E plus capital R E, right. Suppose therefore, we have a resistance in series with emitter, then you will simply say R E plus capital R E. So, this nature of the expression remains essentially same, okay, for a general common emitter amplifier or any amplifier with impedance seen from collector. Is this point clear? Impedance seen from collector therefore, is always equal to, okay, 1 plus R E plus capital R E if you have by R B dash minus alpha into R C divided by 1 plus R E plus capital R E divided by R B dash. This you remember. Now, if it is having R B dash infinity or R B dash very large compared to R E, this point, this will go to 0. R B dash if it is very large compared to R E, this will go to 0 and this will go to 0. What will it become? 1 minus alpha into R C. So, if R E by R B dash is much less than, we have to compare it with 1 minus alpha, 1 minus alpha, because this is the alpha is very nearly equal to 1, 1 minus alpha is also very small quantity. So, when I neglect, I have to neglect it compared with 1 minus alpha. So, if R E by R B dash is much less than 1 minus alpha, then this is very nearly equal to R C into 1 minus alpha. This is the output impedance of a common emitter amplifier. What this is the definition for common emitter. If you have a resistance also in series with emitter, it will be R E plus capital R E divided by R B dash must be much less than 1 minus alpha, then you will call it as a common emitter amplifier. If R E plus capital R E by R B dash is much greater than 1 minus alpha, okay, this is much greater than 1 minus alpha, what happens? This will be negligible, 1 minus alpha will be negligible, this will be Re by Rb dash, this will also be Re by Rb dash. So, this will go towards Rc, which is called common base amplifier, right. So, whether it is common base or common emitter depends upon the relative magnitude of resistance in series with emitter and resistance in series with base, right. If resistance in series with base is dominant, then it is common emitter. If resistance in series with base is dominant, okay, it is common emitter. If it is emitter resistance that is dominant, it is common base. Again, if you have a resistance in series with emitter, you will put this as Re plus capital Re by Rb dash. If it is much less than 1 minus alpha, it is called common emitter configuration, right. If this is much greater than 1 minus alpha, then it is called common base configuration. If it is not negligible either way, then it is a general configuration, right, where the output impedance is always equal to this. So, you can see that output impedance asymptotically reaches Rc and Rc into 1 minus alpha. What is Rc into 1 minus alpha also is equal to Rc divided by beta plus 1, right. So, this is the output impedance of a common emitter configuration and Rc is the output impedance of a common base configuration. And in general, the output impedance is in between. That means, output impedance of these amplifiers, common base or common emitter, will be always lying in between Rc and Rc into 1 minus alpha based on the approximation that is valid here. So, this example illustrates the effect of this non-ideality that is occurring across the transistor, common collector base junction. We had understood a bipolar junction transistor. In today's class, we will be introduced to another important active device. Bipolar junction transistor as well as this active device formulate the family of active devices which are prevalent, covering almost 99.99% of the entire circuitry. So, this important device is called metal oxide semiconductor field effect transistor. Metal oxide semiconductor field effect transistor, which is abbreviated as popularly MOSFET, FET, MOSFET. It is necessary that we understand this active device the same way we understood bipolar junction transistor. So, I will now discuss qualitatively the characteristics of MOSFET. This is the backbone of all our MOSFET circuitry discussion. Let us now understand what a MOSFET is. Consider, let us say, we will take this material, parent material, semiconductor material, which is a wafer. This is the thickness of the wafer, okay. P type substrate it is called, that entire wafer is doped with P type of impurities. So, you start with P type wafer and you would like to fabricate MOSFET, let us say, then that particular wafer, that is the body, it is called substrate or body, okay, is the material over which our device is going to be fabricated. So, this is the substrate material, very important. So, we could start with p type or n type. I have for illustration started with p type substrate. Then it is going to have a n type well here as well as here. This is called source, this is called drain. Okay. You could call it the other way also, this as source and that as drain if it is symmetric here. We have the source contact, aluminum contact here over the source, we have the drain contact, aluminum contact over this drain. These are doped with n type of impurities. So, this is n. When we have the substrate as p, we have the source and the drain here as n. If the substrate is n, then the source and the drain will be p. Okay. Then we have what is called the gate, which is located over a very thin oxide, which is silicon oxide. This is silicon oxide or gate oxide it is called. Typically of the order of 1000 angstroms it is, very thin. Why it is made thin is because you would like to have control over the surface by the gate electrode. So, you would like to make it as thin as possible, so that the control is good. Okay. What does the voltage applied to the gate do with respect to substrate? We will see that. So, this is a thin oxide layer over which we have the gate terminal, gate contact, aluminum again. All these red colored ones are aluminum contacts. Okay. Under this situation, let us understand what happens. We all know that the p type material has majority carriers as holes and minority carriers as electrons. The overall charge of the whole thing is space charge neutrality, right. For every mobile carrier given, okay, there is an immobile, okay, atom left there which is charged in the opposite way, right. In this case, every hole there is a negative charge which is immobile. Overall space charge neutrality is still there in the whole thing. Now, let us see what happens when we apply a voltage here with respect to this. It is like a capacitor we have here between, this is, okay, a conductive material, let us say, and this is another conductive material. In between we have an oxide, okay, dielectric medium, insulator. So, when I apply a voltage here with reference to the bulk or the substrate or the body, we will call this B. So, let us apply a voltage with respect to bulk to the gate. If I now apply a voltage which is positive with respect to this, right, okay, bulk, there will be positive charge all over this, corresponding to which it has to induce negative charge on the surface. How does the negative charge get induced? After all, this entire thing was space charge neutral. So, what is likely to happen is the positive voltage here will cause attraction of first the mobile carriers which are negatively charged. What are they? Electrons. They are the minority carriers here in the p type substrate which are negatively charged, and these negatively charged ones can easily go over to the surface. So, you will have here negative charge induced. There will be limited number of these what? Mobile carriers, because they are minority carriers. You apply further voltage, what happens? Most of these mobile carriers will now come to the surface. Okay. You apply still further, right. Then what happens is the only negative charge that can be induced here is by uncovering certain of the what immobile atoms which are charged negative. That means holes have to be pushed down. Okay. Most of the mobile charge carriers which are electrons have been already attracted towards the surface. Further increase in charge, negative charge, can occur only by uncovering certain of the what immobile charges, negative charges, that is done by driving away the holes. That way you are inducing here. Okay. First, this was positively charged p type. Okay. It was having majority carriers, holes. You will establish a space charge neutrality here. There will be uncovering of charges here, right. Then further increase in this thing will make this go towards okay, and most of the minority carriers will now start getting accumulated here, okay, establishing negative charge, right. And this region now becomes okay, N, okay, instead of P. First what will happen? It will become less P type, okay. Then it will become space charge neutral, then it will become negatively charged excessively, okay, which means it becomes N type. This is called inversion, right. The body was P type, the surface has become N type by applying a voltage here. So, you are able to invert, okay, what the type of material from P to N, or if it is N to start with, by applying a negative voltage here you could make it P. So, this is an important action of the MOSFET on the surface. These are all surface devices. Okay. So, by applying a positive voltage I am able to invert the okay, state of this and make it N type if it is to start with P type. Now, this is open to conduction because this was N and this was N. Now, if you make this N type, what will happen? There is a channel open between source and drain. So, you are set to formulate a conductive channel by applying a suitable voltage from bulb to gate. The width of the channel can be easily controlled, the depth in this case can be easily controlled by this voltage. Higher the voltage, okay, wider it will be, right. So, as to compensate for the positive charge here, it has to open up wider. Right. So, this effect of inversion is an important phenomenon, and the voltage that you have to apply to the gate with respect to the substrate in order to make the surface as conductive as the substrate is called an important voltage, that is called threshold voltage, threshold voltage Vt it is, okay, the voltage that is necessary to make the surface of the semiconductor as conductive as the bulk, okay, by definition is called the threshold voltage. This is the device definition for threshold voltage. Okay. Circuit definition is very simple because it is very difficult. Circuit definition is, okay, threshold voltage is that voltage that will permit a certain amount of current to flow from source to drain, because that can be easily measured, right? Because we would not know what is the doping of this in order to find out what will be the doping of this when threshold voltage is applied. Okay. So, the circuit definition for this threshold voltage is that voltage that is applied to the gate in order to make a certain amount of current, okay, flow from source to drain. Between source and drain, initially there is no current because it was blocked, there was no channel existing. Okay. Because of applying a voltage, you have unblocked it, okay. You have formulated a channel between source and drain, and you are now able to drive a current through the channel. So, threshold voltage is an important parameter associated with this kind of MOSFET. This is called enhancement type of MOSFET. Why? The channel is formed, okay, by enhancing the what? Conductivity of this by applying a voltage. Therefore, the channel can be only formed by applying a voltage, and then only, okay, it can conduct. So, this is called enhancement type of MOSFET. Now, since the channel here is N channel, this is called N channel enhancement type of MOSFET. So, in enhancement type of MOSFET, the MOSFET action etc. will occur only after a voltage greater than the threshold voltage is applied between the gate and the substrate. These devices which are enhancement type of MOSFET are initially not conducting. When the gate is open or when the gate is not connected to any voltage or any gate is connected to 0 volts, all these devices are off. Okay. They can become on only after crossing the threshold voltage. So, they are very good switches, and that is why these are universally adopted in all gates and digital circuits. Okay. So, this has become a popular device in digital circuits because by nature it is off. Okay. When the gate voltage is 0, it is not conducting between source and drain. In order to make it conduct, we have to apply a voltage which is greater than the threshold voltage to the gate. Then we can make it conduct, and the conductivity can be controlled by suitably adjusting the gate to substrate voltage. So, we will therefore say that the current in this case, current IDS, is going to depend upon, okay, this VGS minus VT. Right. Normally, for this operation, the bulk is connected to the source. I mean, we do not want to have too many sources. We would like to minimize the independent sources which are required for biasing to a bare minimum of 1 or 2. So, the bias voltage that is applied between source and bulk is made equal to 0. That means, source is placed at the same potential as the substrate or the bulk. Okay. So, you can connect it together and then apply a voltage with reference to the source. So, this is why it is called VGS. So, this voltage is 0. Now, I am applying voltage VGS between gate and source. So, the current is going to depend upon VGS minus VT. VGS, if it is equal to VT, current is 0, it is completely blocked, there is no channel formulation. The channel formulation occurs only after VGS equal to VT occurs, right. Substantial amount of current can now flow. So, the current is dependent upon the factor VGS minus VT. So, dependent proportional to initially. Now, look at it this way. Once the current starts flowing in the circuit, why will the current flow? Because the potential of D is different from potential of S. So far in this we have assumed that VDS was 0. If this potential also is different, then VGS is different from VGD. If VDS is not equal to 0. So, let us now assume that the voltage applied to the drain is this is VDS, I am trying to make this drain more positive than the source. What happens to now VDG? When VDS was 0, VGS was same as VGD. Do you agree to that? That means the depletion layer width in all these places will be the same, because the voltages are the same. So, whatever happens here will happen at the source end also, right. Same amount of channel will be uncovered in both the ends. Now, my question is, if I apply a VDS, what happens at this end as compared to what happens here? The voltage is positive with respect to this, this is also positive, then means VDG is going to be less than VGS, whatever VGS you have applied, the VDG is going to be less by a factor of VDS. So, this depletion layer width here or this channel width here has to decrease. This channel width will keep on decreasing until what happens? VDS becomes equal to VGS, right, equal to VT, right. Suppose this voltage, that is VDS minus VGS, let us say VDS is equal to VGS, then the voltage applied is 0. That means, you have already gone to a state of 0 voltage between this and this. It has stopped conducting long ago, even prior. That means, when VDS was equal to VT itself, it has got blocked here, right. So, now once again let us see, this is VGS, the voltage VDG is equal to VGS minus VDS, right. So, if VDS keeps on increasing, right, at a point equal to what? VGS minus VT, VDG is equal to VDS minus VDS plus VSG, or this is equal to VDS minus VGS. Is this clear? VDG is equal to VDS minus VGS. This is VDS plus VSG, by then VDS minus VGS. So, let us say VDS was 0, then the VDG is going to be minus VGS, which is all right. The same amount of voltage which was earlier applied here is going to be applied here. VGD VGD is equal to VGS minus VDS, right. So, same amount of voltage as VGS will occur as VGD if VDS is 0. Now, let us say VDS is increasing, it takes on a value which is VGS minus VT. Then what is VGD? This is equal to VGS will get cancelled, this will be equal to VT. So, at that particular point you have only threshold voltage as the voltage applied between drain and gate. That means the entire this thing has been blocked to a certain extent, right. Here when you apply threshold voltage, the channel has just got formulated, right. The channel width will be dependent upon the excess voltage over and above VT that you are having between that terminal and gate. Suppose VT is 1 volt and VGS is equal to 2 volts, then the channel width is corresponding to 2 minus 1 volt, right. Suppose VGS has now become 3 volts, the width is going to be further enhanced by an amount which is equal to 3 minus 1 corresponding to 2 volts. So, this width will be more than the width corresponding to the earlier voltage of 2 volts, right. So, if I have widened it by an amount equal to 1 volt, right. So, let us say VT equal to 1 volt, VGS I have applied was 2 volts. So, I have now a channel width corresponding to 2 minus 1 throughout when VDS was equal to 0. When will the channel get closed? When I apply in the opposite direction a voltage of what 1 volt, because 2 minus 1 is the excess volt. The channel will get closed when I apply in the opposite direction a voltage of 1 volt. Let us again take this. VGS was 3 volts, VT was 1 volt. The channel width corresponds to 3 minus 1 volt. When will the channel get closed? At the drain end, when VDS becomes equal to 2 volts. This VGS was increased to 4 volts, right. The channel width corresponds to throughout 4 minus 1 volt. When will the channel get closed, or we will call this term as pinch off, pinching off the channel, right. So, this voltage at which pinch off occurs corresponds to a drain to source voltage of 4 minus 1 volt, 3 volts. So, if this is 5 volts, it will correspond to a voltage of 5 minus 1 volt, 3 volts. So, that is what is called pinch off point, after which the channel at that point is going to remain closed. So, let us picturize this. What is going to happen when I apply a voltage like this is that the depletion layer width is going to sort of extend here and close the channel. This point where the channel is completely closed is called pinch off point. The pinch off point corresponds to the excess voltage over and above VGS minus VT, that you have applied to cause the enhancement. VGS minus VT is the voltage that has caused the enhancement of the channel. In order to deplete that channel width, in order to close that channel width, you have to apply that same voltage in the opposite direction. So, effectively therefore, VDS that you have to apply at this point, okay, to close the channel corresponds to simply VGS minus VT. Okay. Now, let us see what happens. Initially, I have applied a substantial voltage as VGS. When VDS was 0. So, let us consider when VDS was equal to 0 or very close to 0, what happens. Let us picturize this. When VDS was 0, we have IDS, let us say, versus VDS, let us call it. It is acting like a mere resistance, because this width is going to remain constant throughout. Okay. As I apply more and more of this voltage, gate voltage, this width is going to increase, the depth is going to increase, and therefore, the conductivity of the thing is going to increase, or resistivity is going to decrease of the channel. The resistance of the channel is going to decrease, right. So, this particular thing, as more and more area is uncovered here, right, the resistance, total resistance of the channel is going to decrease. Okay. In which case this is acting like a voltage dependent resistor, or VDR, or voltage variable resistor. By applying a gate voltage, right, I can change the conductance of this or resistance of this. So, one corresponding to, let us say, one value of voltage, this corresponds to VGS1 minus VT. This is the characteristic. Another characteristic, for a higher value of VGS1 than this, VGS than this, let us say VGS2, what will be the characteristic looking like? The resistance is lower. That means characteristic will be having a slope like this. Okay, VGS2 greater than VGS1. This is the characteristic. For VGS equal to VT, what will be the characteristic? VGS equal to VT, what will be the characteristic? The channel is just getting formulated, current is just flowing adequate. That means, okay, almost nearly 0 current. Okay. This corresponds to VGS equal to VT. So, that means by varying this VGS, I can vary the what? Resistance of this. This is an important application of the field effect transistor. It is a voltage dependent resistor or voltage variable resistor. Right. So, now there is something that we have to still understand. We have understood that these whatever has been uncovered here depends upon VGS minus VT. If you want to cover it up, you have to apply a voltage in the opposite direction. For field effect transistor action, like transistor action we discussed, what we have to do is cover it up. That means, the voltage that you have to apply here is of the same polarity as that of the voltage that is applied to the gate. So, that effective voltage between drain and gate, okay, will be opposing one another, right. So, the VDS that I have to apply here in order to close this channel at this point corresponds to VGS 1 minus VT if it is VGS 1, VGS 2 minus VT if it is VGS 2 that I have applied to the gate, okay, so on. So, that means, as I keep on increasing this voltage, the width here of the channel will decrease, this width will remain constant, because VDS is VDG is changing, but VSG or VGS is remaining constant. This has been maintained constant. So, this width here remains unaltered, okay. This keeps changing, this keeps on decreasing. What should happen? The increment value of current, let us say we will go to this, there is an increment current here corresponding to the increment in voltage, there is an increment in current. The next increment in voltage will not give me the same increment in current, because this particular thing has decreased, effective incremental resistance has increased. Follow this carefully. That means, for the next increment in voltage, I will not have same increment in current, it will be corresponding to a lesser, okay, for the same increment in voltage. This increment in voltage can be made as small as you please. So, it will look like a curve rather than a line, right. For the next increment in voltage, the increment in current will still be smaller. For the next increment in voltage, the increment in current may not be there. What is that point? That is the point when the channel is completely closed. The incremental resistance there is infinity, the slope is 0. Okay. This is what is meant by pinch off. Okay. Channel, when it is getting pinched off, it will sustain a current, but it will not cause further incremental change in current for an incremental change in voltage. That is how we have to understand this pinching off. Okay. So, this particular thing will cover itself completely here. Corresponding to pinch off. Thereafter, current is going to remain constant. This is what is called the saturation current. For the field effect transistor, this is going to be the saturation current. Similarly, for the next voltage which is higher, same thing will happen. Next increment in voltage, increment in current is lesser, lesser and lesser, and it is going to get pinched off at a higher VDS, okay, because what is the voltage at which it gets pinched off? VGS2 minus VT. So, the voltage VDS corresponding to which it is getting pinched off is VGS2 minus VT. Here it is corresponding to VGS1 minus VT. So, this is called pinch off. So, this is called the FET action. What is FET action? Causing it to pinch off and letting the current go to saturation. That will happen corresponding to VDS, okay, greater than VGS minus VT. Therefore, transistor is said to be in current saturation region. current is independent of VDS or IDS, which is dependent upon VGS minus VT, and it is equal to K times VGS minus VT whole squared. Important relationship, it is a square law relationship. How is it dependent upon VGS minus VT? In a square law manner. So, IDS is K, a constant factor which depends upon the W by L ratio of the channel. W is the width of the channel, L is the length of the channel, and the width of the channel, right. This is the depth of the channel, right. So, it depends upon W by L ratio. Obviously, current is, it is the resistance, right, depends upon the dimension of the channel. So, W by L ratio. So, K is a factor which is the property of the field effect transistor, this into VGS minus VT whole square. And what is current saturation region? VDS greater than VGS minus VT for N channel device only, right. For the P channel device, this voltage is going to be negative with respect to source, this also is going to be negative, and the threshold voltage also is going to be negative, and therefore, VDS less than or equal to VGS minus VT is the region where the current saturation occurs, right. Is this clear? So, please remember this important point, this region is called triode region. Why it is called triode region we do not have to explain, because the triode characteristic is somewhat like this. So, like a resistor characteristic. So, this region which is VDS less than VGS minus VT is called the triode region. There the characteristic is going to be IDS equals 2K times VGS minus VT whole squared into this into VDS minus VDS squared by 2. There, for low values of VDS, it is directly proportional to VDS, that is, it is acting as a resistance, you can see linear. For VDS very small, it is directly proportional to VDS and also VGS minus VT. Then there is a subtraction, there is a reduction from the linearity, that reduction is a square law again. And this relationship is valid up to VDS equal to VGS minus VT. So, if you substitute VDS equal to VGS minus VT, you should get this value. Substitute this VDS equal to VGS minus VT, you will get this from this. So, VDS equal to VGS minus VT. So, VGS minus VT whole squared minus VGS minus VT whole squared by 2, 2 gets cancelled, you get K into VGS minus VT whole squared. So, at exactly this point, both these relationships merge into one. So, this is the exact relationship below this. When VDS is very small, we can neglect this square law and assume it to be perfectly linear and treat it as a resistance corresponding to VDS by IDS, VDS very small. Then VDS by IDS is equal to 2K, 1 over 2K into VGS minus VT, a resistance. I am putting it as capital R, saying that it is a resistance like any other resistance, not small signal or something. It is actually a resistance like any other resistance voltage can go both positive as well as negative, as long as this square law is neglected. So, with this we are somewhat familiar with the MOSFET characteristics. We will see the other types of MOSFETs like P channel MOSFET, okay, enhancement type. Now, there should be another type called depletion type of MOSFET and junction field effect transistors in the next class.